how were things for the exercise in general? How was the content for the lesson? Was everything clear? And had some of the functions again because they did not work for this week. Did that mean that the functions from one of the previous exercises was not passing the tests, like when you imported it to use it in the exercise number 3? I guess is that what that means? Maybe.
Yeah, I had that trouble too. Like you copy the intro functions and then you try to it worked for the other exercises, and then for this one you run it as normal and then it doesn't work. So you have to I think it's because of the lists. You have to, the sum kind of function is only for NumPy, so you had to change the whole function.
Okay.
To work.
So let's just take a quick look here. I did update the course page, right? This link works. Yeah. So yeah, the first thing you had to do in problem 2 was to import your function from last time, part 0 here. And then there were some tests that should have been run using those lists. Those lists are passed, and then you just call linregress. I'm not sure I see where NumPy is required.
It's just we use the NumPy for last week's exercise. So
okay.
in our, or at least for me, in my equation, I think for the linregress, I use the NumPy function of sum.
Okay.
So you don't have to do loops, but then it doesn't work with lists. So
yeah,
you have to change the linregress function or do a new one or copy it out. Yeah.
Okay. Yeah, that makes sense. I mean, I think essentially, depending on how you wrote your function, you're right. Here, what I've passed in were lists where you may have been passing in only NumPy arrays previously. And so as a result, then, yeah, that would have been the case that it might have not worked properly. And then you would have to modify your linregress function. I think I'm kind of liking how this is going in general with having this little function library that we're building in each week. But yeah, if you notice things about the tests, like not passing certain tests, it might be good just for me to note, in the future for this exercise, that I could add a comment here saying that be sure that your function can use lists, or I could convert these lists to NumPy arrays before passing them into the function. So if you've used the .sum method from a NumPy array, it would still work properly. So yeah.
Well, I'm having a problem with that. I changed my linregress function for lists, and I ran the code. But when I'm trying to print it, it shows this error that unsupported format string passed to NumPy dot. And when I copy paste this code, and I remove this command under print, and I remove this showing the answer in 3 integers, and then I run the code, I get the correct value.
Okay, so it's probably the case that it's expecting this value A to be a single number, and it might be coming back as a NumPy array with one element in it, or a list containing one item. I'm not totally sure, but essentially normally this kind of problem, that if you get something about not being able to handle the kind of string piece of converting this number to a certain format, it's normally because it's expected to be a single number, and it's come back as either a list with one item in it or a NumPy array with one item in it.
Yeah, it shows as a list, this block brackets.
Okay, so if you check, for instance, if you called your linregress function with these 2 lists, and then you checked what the type is of A or the type of B, they should just be numbers, floating point numbers, if the function is working kind of as it would be expected to work. And if it comes back saying the type is a list, then we would maybe need to take a look at your linregress function just to make sure that, it should return just a single number, not a list. So actually, it's possible that that's the issue.
Actually, it's give a one number for A.
Okay.
Yeah, it gives a one number for A.
What's the type of A? If you just use the type function, does it say it's a float or?
I'm gonna check that.
Well, for instance, like if I had, I'll just go to a notebook here. Let's say I had A equals 3.5. I could store that in memory. And then if I used to use type and A, it tells me that it's a floating point number. If I put that in square brackets and then check it, it says that the type is a list. So my guess is it's something like that. It's either coming back as a list or a NumPy array with one item in it. But that's just a guess.
I'll try it.
Yeah.
Check.
But as a reminder, yeah, this exercise number 3 is not due until this week, Wednesday. I think it was Wednesday at 5 p.m. So you still have a couple days on this because I felt a bit guilty putting it up so late. So if you're having issues like this, please let us know in Slack or send a message. So I do realize that some of these tests might be operating slightly different than the tests that were there in some of the earlier exercises, like in exercise 2, maybe you could pass the tests and they don't pass here. It's possible that I've written the tests to be a little bit too restrictive. And that's certainly possible. But I've also kind of written the tests assuming that the function would work to give back what I would say is the kind of logical expected value to come from here, which would be a number for A and a number for B. Same thing for chi. It should be just a single number that comes back. So if you're having issues with that, please let's talk on Slack or elsewhere. But I saw a few extra comments here. Exercise is done, still something to think about to the plots. Example, the axis titles and units. Yeah, exercise was difficult, but doable. And the length was okay. All right, well, that's good to hear. This is a totally new exercise, which is part of the reason why it took me so long to get it posted. But the idea was really just to focus on exploring the diffusion equation a little bit. So I do understand. I was asking you to do a fair amount of work here, especially with Dodson's equation. That's sort of a challenging coding exercise to work through to create your function for using Dodson's equations and this kind of idea of iterating to find a solution and things like that. So yeah, if you've gotten as far as getting that working and you're getting some of the plots, of course, you can fine tune the plots in the end. And I think you should be in good shape. Was there a question here about the axis titles and units for the plots, or is it just like you just need to simply do them? Because basically for the first problem where you're creating plots, for instance, here, you're going to have plots where I guess you're directed what you should put on the axis. So the distance on the x-axis and concentration on the y-axis. In this case, the distance does not have a dimension associated with it. It's not like meters or something like that. It's just simply a unitless distance. So you can just report that as distance on the axis label and concentration on the y-axis. So you can just list those as distance and concentration for the first problem because we don't deal with specific units there. It's just kind of getting a sense of how this diffusion equation is working. In the second example, in problem number 2, I guess down after you create your Dodson's equation and find out how it works, you're asked to make a plot with cooling rates on the x-axis and closure temperatures on the y-axis. Closure temperature, of course, is going to just be in degrees Celsius, and the cooling rate would be in degrees Celsius per million years. So it's just like what you've put in as an input value here. This looks crappy in GitHub's preview of the notebook, but you see cooling rates from 0.01 to 100 in 101 steps. Those cooling rates are going to be in degrees C per million years. So you can see, for instance, the unit here for the cooling rate. And then I think it should be that the plots that come after that, grain radius is given in microns or micrometers. So you can list the grain radius as micrometers. And I think otherwise, the last plot that you have to make is a little bit different. That's a bar plot, so it's only going to have a closure temperature. I believe that's the case, yeah. So if there's not anything else about this exercise number 3, I'll just remind you that you can go and talk on Slack, or you can get in touch with us otherwise if you have questions still, and you have until Wednesday at 5 p.m. to complete the exercise for week number 3. We will have exercise 4 assigned today. The plan for exercise 4 is that it would be due at the normal time next week. So there'll be a little overlap between these 2 exercises, but I don't want everything to kind of get like behind. So we'll see if things are really kind of problematic on Friday in the exercise sessions. If it seems like chaos, then we can always possibly extend the deadline if needed. But the plan would be for exercise 4 to be due at the normal time. So it started the lesson 5 in a week from today. But yeah, if I don't see, I just check one last time. Any last comments? I don't see anything here. We'll go to exercise or to lesson number 4. My apologies, the course page, I didn't get a chance to sync the changes to the live, like regular version of the page. And this landing page is still a little bit out of date. I was updating the exercise to make sure that was ready for today first. And I didn't get a chance to update the course page yet, but I will do that as soon as or shortly after we're done. Certainly by this evening, I'll have it updated, and then you'll have the links to today's lecture slides and things like that available from the course page. But as far as the topic goes, it is basically the same thing that's described here on lesson 4 from the last time the course was given. It's about the advection equation. The last time we did advection, we dealt with the stream power river erosion equation. We're not going to do that today because we're going to do something that's better in a sense for combining what we have seen last week with the diffusion equation and something that also relates more directly to thermochronology, which we will be revisiting toward the end of the course. So you'll see kind of what's coming up there in the lesson for this week. The lesson itself is probably going to be a little bit shorter than last week. I think I'll probably not take quite as much time for the lecturing piece, which is maybe a good thing because it means you would already potentially be able to get started on exercise 4 if you would like, or if not, that I would be able to hang out here in our Zoom session until the end of the normal time and answer any questions you might have about exercise number 3 or content from week 3 in the course. But yeah, I think what we'll do here is maybe I will start us off with our first bit of the lecture for today. And you can just ask questions in chat if you have any. And basically, we're going to meet the advection equation here. We'll look into it in a little bit more detail in a couple different forms outside of this lecture, but this is basically just to kind of introduce what the advection equation is, what it can be used for, and how it relates to some of the earlier topics. This slide title is still the previous year's title, so it's a little bit different than advection of the Earth's surface, but the point is still that we're talking about the advection equation. So 2 points mainly for the lecture here. One is to introduce what the advection equation is, and the second point doesn't really relate to us so much, although we'll see an example related to river erosion, but we won't go into detail. But the equation works very similarly to, well, several other applications of the advection equation. So let's talk concept here. When we talk about advection as a process, it's essentially just a fancy word for the lateral translation of some quantity. So what we're looking at, for instance, here in this little animation that's playing is sort of two-dimensional mantle, upper mantle convection model. So you can see these kind of plumes of material sinking down periodically. Those would be like a subducting plate sinking down. I guess this is probably the scale of the whole mantle, not just the upper mantle. But you can see here that things are sort of stagnating at the mantle transition zone, the boundary between the upper and lower mantle. And occasionally there's a sinking of material down into the lower mantle, and that's a plate that is pushing its way down into the lower mantle, being mixed in with the rest of the material there. Here we are advecting mass. So it is the mass of the plate sinking down and moving that's being considered. But what we're actually looking at in the field is the temperature of that mass. So this is basically these cold plumes are shown in blue of the material that's sinking down at the mantle transition zone and kind of accumulating there until it's able to sink into the lower mantle. And of course, if you follow any one of these blue plumes as they sink down, they get warmed up by the surrounding mantle material and become red, which is essentially because the interior of the Earth is hot and heating that material in the mantle. Overall, it looks like there's a trend in this particular model that the mantle is always getting a little bit warmer, which is kind of odd. But basically, as it's mixing the material around and moving, flowing within the mantle, things are heating up, and that's what's changing the colors here, which is essentially a measure of temperature. This could just as easily be advection of some kind of chemical quantity. So if we were looking at this from the perspective of geochemistry, this could be a mass of material with a given chemical composition going into the mantle and being mixed, and then the composition of that plate that has sunk down is being diluted by the composition of the surrounding lower mantle material into which it is being mixed. But yeah, transfer of heat by physical movement in this case. So it's not just like we looked at with diffusion of heat, where you have, atoms that are sitting in a crystal lattice vibrating and the vibrations are transmitting energy. Here we have actual movement of the material, and this is a sort of type of convection that's the word advection is often applied to heat transfer in solid materials, but it's a general term. So as you'll recall in the lesson from last week, we met the diffusion equation. There were two pieces that went together with it. There was this flux that's proportional to a gradient. So there's our flux term Q. Here's our diffusion coefficient D, and then we had our concentration of atoms of A and some distance over which they were changing in concentration. So that's our gradient term dC dx. Q is our flux. And the other half of our diffusion equation was this conservation of mass piece. So any change in flux results in a change in mass or energy. So if dq dx changes, then there's a change in concentration over time. So if we make dq dx bigger, and this is a negative sign here, so if this is bigger, then we might expect the concentration to go down more, and so on. We also went through the process when it came to the exercise of plugging these two equations in together. So basically, if you take the Q here, that's equal to this d dc dx term, and plug it in for the Q here, then you end up with the diffusion equation that looks like this. Just says basically the change in concentration with time is equal to this diffusion constant, d, times the second derivative of the concentration over some distance dx. So in this, if you want to talk the talk, this would be the curvature of the concentration, the change in the gradient. And then here are all of our different letters spelled out below. Now, we're going to be dealing with the heat transfer equation this week, but I'm just going to kind of flip back and forth between these two slides for just a moment, because the diffusion or heat conduction piece of the heat transfer equation looks a lot like what we were just looking at. In fact, it is a diffusion equation. So we have a change here in temperature with time being proportional to some constant or equal to some constant kappa. That's the thermal diffusivity times the second derivative of temperature over some distance. Here, I'm using z as a distance for depth, because that's often what we're most concerned about in the Earth. But if you kind of flip back and forth between the two equations, you'll see that basically if you replace the C, the big C, with a T, so change in concentration to be a T for thermal energy, and you replace the D with a kappa, you basically have the same equation that we just saw, the diffusion equation. This is a nice example because we already know a little bit about the diffusion equation, and we can put this together with an advection equation to allow us to simulate heat conduction and heat advection together, which is a useful thing to do, especially when we start talking about thermal chronology. So here we are now meeting the advection equation. It looks quite similar in some ways to what we just saw. Here we have a dt term. So this is change in temperature over time, being equal to some v, this is a velocity term out in front, times the change in temperature over some distance dz. So looking at these two side by side, you can see that they're somewhat similar, yet importantly different constants. So we had kappa here. Now we have some velocity vz, and we had a second derivative here for our gradient term, and it's only a first derivative for the advection equation. Basically, that's spelled out right here. So two key differences: change in mass with time is proportional to the gradient rather than the curvature. So here we have this dt being proportional to or equal to kappa times the second derivative for the diffusion equation. Now we only have a first derivative for the advection equation. And our coefficient here, Vz, has units of length per time rather than length squared per time. So you might remember before when we were dealing with concentrations, I guess, well, I don't know whether we saw the units of the diffusion constant except when we started dealing with it with exercise number 3, where we were then dealing with the units that would have been something like meters squared per second, for example. Length per time would be something like meters per second, which, as you will immediately recognize, hopefully, would be a velocity. So that is why we have this V labeled here as the letter V, because that's short for the velocity in the Z direction. So Vz is our velocity term here. Now, I have found some okay visualizations for this heat transfer thing, but it's actually a bit easier to look at this in the context of river erosion, which is why I did this before. It works exactly the same way for river erosion as it does for heat transfer. So again, sorry to jump to a slightly different equation, but you'll see this slightly different equation is almost not different at all. So here we have temperature when we're dealing with heat. When we talk about diffusion with respect to a river, we have here elevation or height. So change in height of the river channel being equal to some kappa constant. Again, this is another diffusivity type thing, but it's diffusivity of rock. It's a little different. And then here we have the second derivative of elevation over some distance instead of second derivative of temperature, but basically almost exactly the same thing. And the same goes for the advection, where we just have some constant labeled C here out in front in this case. So The reason I want to show this is because this diffusion profile will look somewhat familiar to you, I hope. So this is like a river channel profile. So you can imagine some river flowing down from some like plateau or something like that, goes over a steeper piece of the river channel and then flattens out. So we're kind of just looking at like a cross-section view of some river flowing down a slope and flows over the steep edge, speeds up, and then flows down along another more gradual, gentle part of the river channel. Now, over time, if we let the river sit there and just move material around in such a way that we imagine the river is made up of a sort of bed that contains grains of sediment, could be rocks, sand, whatever. Over time, what you're going to see is that steep kind of piece of the river will gradually get more and more gentle. This is what we'd call an alluvial channel, meaning it's covered in alluvium. And what's happening is essentially that channel is the steep gradient you had in the channel is getting shallower and shallower. You might remember with diffusion equations that diffusion reduces gradients. In this case, it makes our river channel be less steep than it was before. And by time T3, it's become kind of a nice gentle river. Same thing happens with temperature. When we talked about the examples of that in last week's exercise, if you put something hot and something cold together, you have a very high gradient in temperature when you first touch the two hot and cold things together, but over time, that difference becomes more and more gradual. If we take the same example for a river that is advecting or experiencing the process of advection, this is the same kind of idea, gentle, high elevation piece of a river channel going over a steeper part of the river channel and then flattening out. With advection, what happens over time is that the channel shape and the channel geometry doesn't actually change in terms of its profile. It just moves off to, in this case, to the left. So the original shape that we had here, this kind of like very flattened out Z or flattened out reverse S shape, however you want to think about it, is the same that's in place at time 2. It's just moved off to the left, and the same thing would happen then at time 3. And this typically is what's occurring in a bedrock river channel where there's not a bunch of sediment armoring the bed, but instead you've got water and things in the river chipping away at the bedrock itself. You maintain the steep reach and you see lateral migration of the river as a result. So this process of advection isn't changing the channel steepness in any way. It's just moving the river off to the left, which typically would occur in the form of like a river incising and carving a valley upstream over time. In terms of heat transfer, this would be basically the same thing as just saying, like, let's move some hot rock from somewhere deep in the earth up toward the surface and not change its temperature at all. That would be advection. So I think I've already made the point here about the differences between diffusion and advection. The only other distinction here with our advection scenario is that there is no conservation of mass in this form of the equation. The river is just moving off to the left. Here, for every part of this river channel that gets decreased in elevation, there's some other part where the elevation increases. So in other words, between times 1 and times 2, you would see this sort of upper part of the river channel move down, which makes the gradient lower, but you'd also see the lower part of the river channel move up, which is conserving mass. Hopefully that makes some sense. I apologize. The river channel example is not perfect, but the figures that I found are just better for this than for trying to do it with heat transfer. But that's kind of it for this quick introduction to the advection and diffusion equations. And since that was relatively quick, maybe someone willing to say something in chat about what's different between these two equations. What are some of the important differences between the advection and diffusion equations? Do you remember?
Well, one has the double derivative and the other one diffusion has a double derivative and advection only has one.
Yeah. So that's one of the things that we saw here when we look at the difference between diffusion and advection here. So we've got second derivatives with respect to whether it's temperature, whether it's concentration, whether it's elevation, whatever the situation is. For the diffusion equation, we have a curvature dependence instead of a gradient dependence, which is what we have in advection. There's one other thing on this slide that's an important difference between the diffusion and advection equations. Anybody want to point that out? So the thing here is that in this case, there's no conservation of mass or conservation of energy with the advection equation. So with a pure thermal advection equation, it wouldn't necessarily be that interesting to look at, but it would not require that over some thickness of the model, whether it's crust or lithosphere or whatever scale you want, that temperature or energy would be conserved. So they work a little bit differently from one another, but it's not too bad to hook these two things in together. So let's go here for a moment. Just take a look at the next thing on the lesson about solving the advection and diffusion equations. And again, this will be available on the course page live in some point this evening. I've already introduced the advection and diffusion equations in some sense. They're reintroduced here. If you want to read through this, it's just another kind of verbal explanation of the two equations. But what we saw before was the heat transfer case for diffusion, the heat transfer case for advection. And because both contain a dt term in them, we can simply add these two values together and say that, yes, if the change in temperature with time when diffusion is active is equal to this, and the change in temperature with time is equal to this when advection is active, if both processes are active, then it's simply the sum of their two activities that would result in some change in temperature, for example. So this is what's called the advection-diffusion equation. It's commonly used for heat transfer problems where you want to simulate both heat conduction and some kind of movement of material. So whether you have sedimentation, which might mean sort of filling in some basin with material and causing the basin to sink down, or whether you have something like erosion where you're uplifting a landscape like in a mountainous area and eroding away the rock on top. These two terms would be essentially necessary to calculate what temperatures would be in the crust in either of those settings. So we combine them together here. We end up with this generic advection-diffusion equation. This is in one dimension because we only depend on depth z in this case. So this is relatively straightforward in terms of just adding these two things together to get this equation. Solving this is not necessarily so straightforward, but we can make things easier at first, which is to make a steady state solution. So what steady state means is that the temperature would not be changing with time, or in other words, dt, so change in temperature over time, goes to zero. If that's the case, we just make this term on the left side be equal to zero, do a little bit of rearrangement, and we end up with something here saying that the second derivative of temperature with respect to distance z is equal to minus Vz over kappa times dt dz, which can be rewritten another way like this. This is basically the same equation, just slightly repackaged to take this one derivative and put it on the outside. And what you can see is that you have a dt dz here and a dt dz here. This is a differential equation. And thus, from this point, we need to come up with some way of solving it, and that is to find some equation that will fit this kind of behavior in order for us to be able to deal with it. And there's equations of the type that says some functions equal to a constant times e to the cz. So you don't necessarily need to worry about that so much, but that's essentially the kind of template function that we can use. And if we start plugging things in here, we can end up solving our equation for different examples. So if we assume, for instance, that one of the conditions we have to meet with our equation is that the temperature gradient at the surface must not change. So maybe it has to be 20 degrees C per kilometer or whatever you want as a sort of boundary condition. We can then solve our equation, in this case for a letter G, which would be this gradient value. And you come up with something that looks like temperature is equal to this stuff on the left side. So G kappa over VZ times E to the minus VZ times Z over kappa, plus some constant of integration C1 that we don't yet know. But we can solve and find that pretty easily, do a little bit of rearrangement, and we end up with this equation here, which is the 1D advection-diffusion equation solved for a case where the surface temperature is 0, and we assume a constant thermal gradient G at the surface. You'll use this equation in problem 1 of the exercise this week. So this is basically just got some of our familiar terms in here. Our G is the gradient, kappa is the thermal diffusivity, and VZ is the velocity at which the material is being advected. And then it's 1 minus E times some of that same stuff on the last term there. There's also an example that's just shown for a different scenario, which is to assume that the temperature is fixed at some depth. So instead of assuming a constant temperature gradient at the surface, we could also solve this by assuming the temperature at some depth is equal to TL. So this is the temperature at depth L. And if you do that solution, you end up with an equation that looks like this. It's also a nice one for making plots of temperatures in the crust, for example. So I would suggest that for the exercise for this week, you might want to just read through this kind of derivation once again, just to make sure you kind of understand where things come from, understand that the constant gradient we're talking about here is a geothermal gradient, and it has to be met as part of the solution to this equation. So no matter what you do, if you put in this equation and you say, I want to calculate the temperature, what you would find is that the temperature gradient at the surface would be equal to the letter G. So that's the way in which the equation has been solved. It's one of the conditions that must be met. You would also see that if you put in a depth of 0, that you should end up in a case that your temperature you get back is equal to 0. So you would end up with something like this being 1 minus 1. And anyway, you'll end up with a temperature of 0 because the 1 minus 1 term gives you a 0 there, and anything you multiply by 0 will also be 0. So your temperature at depth 0 at the surface would be equal to 0. There's a couple other things in here you can look through if you'd like, but just in preparing to do the exercise, or if you get stuck in the exercise, it might be worthwhile to read this through one time. At this stage, I think maybe we can take a quick 5-minute break, and then we have a short second lecture, and then you guys I'll walk you through the exercise and you can get started on that. But let's come back at it's 3:01 right now. So let's continue at 3:06, and I'll see you in 5 minutes.